So today's a big day in our syllabus because it's the first time we're going to do properly nonlinear methods. Moreover, we're going to cover ensemble methods, which will give us gradient boosting, which is one of the most powerful and popular machine learning methods used today. It wins categorical competitions routinely. I'd say gradient boosting and neural networks are the two most commonly used, kind of most powerful machine learning techniques. And we're going to get to gradient boosting today for sure, and likely neural networks next week. All right. So the nonlinear method at the core of all the methods for today is the tree. And we'll start with a discussion of classification and regression trees. So trees. So let's do a little vocabulary first, just to get a rough idea of the structure of a decision tree. So we have a tree of nodes, looks like this. The top node is called the root node, and that's where our decision-making process starts. And these other nodes are called internal nodes, or in our context, split nodes. And the last thing is that the nodes at the bottom are the leaf nodes or the terminal nodes. So we'll need some of that terminology as we go. Now, how does this thing work very roughly? We have a binary decision tree where we start at the top, and at each node of the tree, there's a question to answer. And it's a yes-no question. And if it's one answer, you go left, and if it's the other answer, you go right, and you work your way down the tree to a leaf node. So for instance, here we'd say, is the top part of this picture blue, yes or no? If yes, go right. If no, go left. Next question, is the bottom part blue? If yes, go right. If no, go left, etc. And when you get to the leaf nodes at the bottom, there'll be a prediction that you use, a classification if it's a classification problem, or a number if it's a regression problem. All right. So this is all just very high level, but let's get into some specifics. So here we have kind of two representations of a binary decision tree. Yeah. And we're looking here at two different features, and they're x1 and x2. So over here, this is our tree. We'll come to the picture on the right in a moment. And this tree defines our prediction function. Given an input x, or x1 and x2, what's the output going to be? And the first node is associated with this question, is x1 less than or equal to t1? All right, it's a question about one feature. And if it is less than or equal to t1, then we go left, and otherwise we go right. And then you can see each of these subsequent internal nodes, there's a question answered. You could read this condition as a question. Is it true that x1 is less than or equal to t3? If yes, go left. If no, go right. So given any input, we can work our way down the tree to a leaf node. And each leaf node will be associated with a prediction, something in our action space. All right. So that's kind of an algorithmic understanding of what this tree is doing on the left. Now on the right, there's another important view of what a tree is doing. And what's going on here is that every leaf node of the tree corresponds to a different region of the input space, right? So any input point, any point of input space that ends up, for instance, in this leaf node, which we've called R4, has had to answer has taken a certain path down the tree, and thus has answered certain questions in a certain way. So to end up in R4, we know that we went right, so x1 must be greater than t1. We know that we went right again, so x1 must be greater than t3. Then we went left, so x2 must be less than or equal to t4. So these are conditions on x1 and x2 that describe any element that ends up in R4 when it's fed down the tree. And so what we have on the right is the partition of input space, x, into the regions, each region of which corresponds to a leaf node, a terminal node of the tree. All right? So we think about a tree as partitioning our input space. So today we're going to talk about trees in some generality, but we'll restrict to binary trees, which kind of the most common and most used. We can have multi-way trees where you split with more than two, but we'll not talk about that today. So the restrictions we're going to have, one is that at every node, our decision only depends on a single feature. All right? Again, you don't have to have this restriction, although this is the most common by far in practice. We're going to have two types of questions that we ask at each node. One is the type we've already seen in the previous slide, and it's for continuous variables. And we'll have these inequality type of yes/no questions. Is a particular feature less than or equal to a particular value? Yes or no? For discrete variables, we'll talk about that towards the end of this module. Discrete values can take lots of possibilities, no order to them, and we can split on any subset of possible values of the categorical variable. So if the categorical variable is color, we may have red and green go right, and all the rest of the colors go left. You can split the categories in any way. All right. Just for reference, there's other types of ways you can split. You can have oblique decision trees, where instead of focusing on just one feature, you allow a linear combination of features and a threshold. So you can, rather than these rectangular axis parallel regions, you can get regions with arbitrary linear boundaries. There's sphere trees. Never seen those used in practice, but they have been described in the literature. All right. So any questions on the setup for the decision trees? So we're going to dive in first to the somewhat simpler type of tree, the regression tree. Classification has a little extra complexity that we'll get to. So here again is, now we've started with the partition of the input space given by the tree on the left. And what we have on the right is what happens when for every piece of the partition that the tree gives us, we assign a particular value to predict. So just to reiterate, in a tree, you work your way down to a leaf node, and then anything that ends up in that leaf node gets the same prediction. Right. So here, you could see that we have this like piecewise constant function. The input space is x1 and x2. It's illustrated here. And each region of the input space has now a height, which is depicting the output of the tree for any position in the input space. Clear? Yeah. All right. So the decision tree gives us the regions. Partitions are spaced into the regions. And mathematically, I just define what we mean by a partition, just to rehash, is that the regions, if you take the union of all the regions, you get the full input space. And two regions have no intersection. Okay, so the regions are not overlapping. All right. So given this partition, suppose we already have the partition given by the tree, we could ask, well, what are the optimal values to predict for each region of the tree? So we can write our prediction function in this way. F of x is this linear combination of indicators for is this input in a particular region. So you'll note that this is the indicator that x is in Rm. Since the R's partition the input space, any given x is in exactly one of these regions. And so all these terms are 0 except for one, the region containing the input. And so for that region, the output of the function is C sub m. Right? So C sub m is the value corresponding to region R sub m, right? To one of the regions of given by the tree partition. All right, so the question is, how would you choose C1 to Cm? So what do we have to decide on to know how to choose the C's? We need to introduce something additional. A loss function, of course. So let's go square loss for regression. And so in this case, it should be clear that on the training data, the best thing you could predict to minimize the average square loss would be the average of the values of the training set that fall into a particular region. Right? So The predicted value is, you look at the average of the y's over all the elements of the training set that fall into the particular region. So if yeah?
So these regions, are they, each node of the tree has one region, like the 1 through m?
That's right.
Like all of the steps in that tree? Like
I see. So we're only considering, so there's a few things. So in some sense, yes, it's true that every node of the tree, internal nodes included, correspond to some region of the space, because to get to this node, you had to answer a certain question. x1 is greater than t1, so you're in this node. But when we talk about the partition of the space, we're only talking about the leaf nodes. So the leaf nodes, the last nodes of the tree, those partition the space in that any given input, element of input set will be in exactly one of these regions. Right? Yeah. So a higher level internal node may correspond to the union of two leaf node regions.
So in that sum of indicator functions, only one will be active.
In this sum of indicator functions, only one will be active. That is exactly correct. Go ahead.
The next, if you tick forward where we just, so this seems reasonable given that I have this set of partitions, R1 to Rn.
Yeah, if you have the set of partitions, this seems like the right thing to do.
But it seems like that's the magic. Is like,
How do you find the partition?
yeah, it seems much more important that I like am averaging the right set of points in a partition than I.
Right, it seems a lot harder to get the partition than to figure out what to predict in the partition.
Yeah.
Yeah, absolutely. Good thing there's some lecture left to go. All right, we'll get there. So, all right, a brief comment about this. How much do you split? If you can keep splitting your regions finer and finer until you could put every unique input value into its own partition, and then you might worry, and rightly so, about overfitting. All right. So we're gonna need some way to control the complexity of our trees so that we don't fit more than we should. So a few common ways to control complexity of your tree. In CART we'll talk about a number of times. It's, I guess, maybe the first, maybe the most successful of the tree type algorithms. And they recommend the number of terminal nodes, the number of leaf nodes, as a measure of complexity. But a lot of software uses the depth of the tree. So let's say we don't want a tree that goes down more than four steps, for instance. So mostly in this lecture, we'll talk about the number of terminal nodes as our measure of complexity. But as I said, it could also be depth or something like that. OK. So if you define a measure of complexity, such as the number of terminal nodes, a natural question is, what tree fits my training data as well as possible, subject to my constraint on the complexity? Right? That would kind of be the natural empirical risk minimization type of question to ask. The issue is that finding the optimal binary tree subject to this constraint complexity is computationally intractable. There's various theorems saying that this is NP hard. So we're going to need some kind of approximation here. So we can't hope to find the truly optimal tree for a given complexity. So we will try greedy algorithm. What's a greedy algorithm? In this case, we're going to build up our tree kind of one split at a time. And at each point, we're going to decide the split that, in some sense, we think gives us the best chance of having a good tree eventually. But we're not going to do any searching ahead. We're not going to literally probe several splits ahead to see what split we should do now. So greedy essentially means no look ahead. All right, so given an input space that's RD, for instance, so D features, in that case, and we're going to restrict to splitting on single variables, single features. So there's going to be D possible variables we can look at to split at every node. And then for any possible splitting variable, we have to choose the threshold, like at what what do we compare it to go right or to go left? So those are called the splitting variable and the splitting point, split point. So anytime we have a collection of data, say in a node, we want to decide whether we split it. It has to do with complexity control. And then if we're going to split it, where do we split it? And on what variable do we split it on? OK. So once we've decided, just to develop a little bit more notation, once we've chosen a splitting variable j, so the jth feature, and what we want to compare it to, the split point, then we can define the regions that correspond to that split. So R1JS and R2JS. R1 and R2 will be the two regions that this particular split divides the space into. So if the splitting variable is xj and the split point is s, R1 will be everything with xj less than or equal to s, and R2 will be everything with xj greater than s. All right. OK. So this is for the kind of the first split of the tree. Right? So once we have decided once we have a proposed first split of the space, now we have our two regions. And now, as we kind of argued before, it's easy to find the prediction for each of those regions. For regression, you just take the average of all the training elements that fall in each of those two regions. All right. So still, how do we find where to split and what variable to split on? Well, we can write this kind of in an objective function form. So we have our square loss, which we've divided into two pieces. We sum over all the training points that fall into region 1. And we look at the square loss there, and all the training points that fall into region 2, and the square loss here. Well, we've already plugged in what we know to be the right prediction in each of these regions. So the average of the training points in region 1 and in region 2. All right. OK. So all right, so let's consider splitting on the jth feature. So let's draw some pictures here. All right. OK. All right, let's make this really easy. And suppose we only have one feature, all right, for starters. So if we only have one feature, all that we have to do to decide is where to split on the feature. So here's a set of 6 training points. The input is x1, and it's a regression problem, so the output is the y value. We only have one feature, so which variable we split on is nothing to decide there. We need to decide where to split here. Now, just to see where we're headed, suppose somehow or another we decide to split right here. All right. So then our two regions are, let's suppose this is S. Our two regions are x1 less than or equal to S, that's R1, and x1 greater than S, that's R2. Clear? All right. So now, for each region, we get to choose a prediction. So what shall I predict in region 1? Yeah, somehow the average of these points. So that's maybe about here. So anywhere in region 1, I'm going to predict something like that average. And over here, I'm going to predict something like this. All right. So in our notation, this level is C1 hat, and this level is C2 hat. Clear? OK. Great. Now, here's a proposed prediction function. We can figure out its loss. We can look at the square error, average square error on its predictions. All right? Now we get to the question of where should we split. This is just a possible split point, but of course we could split anywhere here. So think about what the function would look like as we change the split point moving over. So if the split point is here, what's our function look like? Our prediction function. Our prediction function is who knows to the left of this point, but to the right, it's the average of all these points. So it's just constant over this entire region. As we move to the left, eventually the split point will cut off this one point. All right? And what's going to be the prediction to the left in that case?
Exactly that.
Be exactly that point, and to the right, the average of the remaining points. And we slide over. And how many unique prediction functions are we going to get from this process?
The number of points?
Is x continuous?
X is continuous, yeah, but we have 6 points. OK, so if we're here, we have 1 that's the constant function. And then we get maybe another one, another one, another one, another one, another one. And here again, we have the constant function. Right. So 6, one of them isn't very interesting because one is just the constant function. So if we're thinking about splitting, if we're splitting on this variable, being over here is not a split, really. It's not a split at all. The points do not get split into 2 different regions. So really, we only have to consider 5 split points. Now, if we split here, now there's infinitely many points we could split at between any 2 adjacent training points, right? The training loss doesn't change, right? The prediction function changes, though. When you get a new point, it'll be, all right. So you get the idea. The convention is you only split kind of halfway between adjacent points, right? That's kind of a convention. So I think, so you guys should start to see how this can be done. If you want to decide where to split on feature x1, you could sort the values of x1, for instance, and then consider splitting kind of between each adjacent point in that way. For each possible split, compute your square error, right? And choose the splitting point that gives you the minimized square error. All right. So that's how you do it for one feature. Now, how do you choose which feature to split on?
The feature that gives the maximum information.
Too far ahead, too far ahead. How do you choose, in this setting, how would you choose what feature to split on? Yeah?
You just brute force and try all of them?
Brute force to try them all. For every feature, you figure out what the best splitting point is by sorting on that feature and trying each splits. And then you do that across all features. And for everything you've tried, you're finding the square error on the training data. And you choose the feature and the split point that gives you the minimal loss, the minimal square error. And that is how you choose where to split in the regression case. Great. Let's see how many slides that got us. One. So, yeah, question?
So then, each of these epochs, or whatever that whole algorithm you just described.
So I just described how to. So starting from scratch, we have a bunch of training points. What's the first split? That's what we've described so far.
So,
I mean, let me get one slide ahead. So we start with all the training points. We do the algorithm just described. We find this feature to split on. We find the point to split, the splitting point. We do the split. So now we've gone from, so we have a root node, and then we've split it once, and we have R1 and R2. All right? What now? Now we iterate. Now we find all the points that ended up in R1, and we again consider how to split it. We do the same algorithm just on the points in R1, and the same algorithm just on the points in R2, and we iterate recursively until we decide to stop splitting nodes. OK, now your question.
Just an observation that each of these steps seems to be a function of the size of the training set.
Yeah, so each of these, yes, that's correct. So what's the computational cost, would you say, like given the algorithm we've described, in terms of the size of the training points in each node when we're deciding to split? Yeah, so there's a sort, so there's like an n log n. And then there's a number of features, because we have to sort that many times. And everything else is dominated by that, right? Yeah.
But it's super parallel.
It's super parallelizable in that you can look at each feature separately. That's right. You could sort each feature independently.
So how do you decide which feature to make a decision on first? I guess we sort of like, we're like, oh, suppose you want to split on the J feature. And then let's action.
Yeah, so the question is, so again, how do you choose which feature to split on? So the process was, for any particular feature, you could figure out where to split that feature. And once you find that, you can figure out the loss for that feature and that split. And then you do the same thing for every feature. And you see which feature and the optimal split point for that feature gives you the minimal loss. So it's an exhaustive search over all possible features to split on and all splitting points where we constrain to looking at the halfway point between adjacent values.
Is it possible that choosing the mid-loss for one splitting step will result in an increased loss for the next one? So like in terms of like the global.
Yeah, so the question is minimizing, finding the best possible split for a particular step that may not optimize the overall objective of minimizing the loss of the tree you end up with. That's absolutely correct. So that's why this is a greedy algorithm. All right, so that's the rough idea of how we build trees. Still a bunch of points to make. Any questions before we dive in some more? All right. So first there's the issue of overfitting. When do we stop building these trees? When do we stop splitting our nodes? And so the trade-off is obvious. If the tree is too big, we might overfit. If it's too small, we'll miss certain patterns. So I mentioned you can limit the depth of the tree. You can also require all leaf nodes to have at least a certain number of training examples in them to keep any given node from splitting too much. Or you could say, I'm not going to split a data point unless it has at least a certain number of training examples that fall into that node. These are all different parameters you'll see in software. But the one very powerful approach that seems to have worked very well empirically is called backward pruning. It's the approach used by CART. CART stands for classification and regression trees. It was invented by 4 superstars of machine learning. Bryman being the head author, the first author, Friedman, Ocean, and Stone. Those names will come up again in different parts of this lecture. So backward pruning is where you build a really big tree, really deep, and then you gradually prune it back. So the way that works is pruning a split is, suppose we split R1 more to R3, R4. So pruning a split would say, you know what, this split of R1 into R3 and R4, it doesn't really help our objective that much. Let's drop it. And then we go back to R1 as the leaf node. So backward pruning, it's kind of a greedy pruning where you figure out what split at the very bottom can I eliminate with the least penalty in terms of increasing my loss, right? So if you eliminate a split, your loss will go up a little bit. But let's find the one that reduces it, that increases the loss the least. And we can iteratively prune back all the way back to the root node. And you kind of get a sequence of trees. And then you can choose which one of those, which pruned version of the tree does the best on validation data or something like that. So that's kind of, in a few words, what backward pruning is. I won't go in more depth than that today, but I left some slides at the end of this lecture in an appendix if you want to study this pruning more carefully. It's not pervasive. sklearn doesn't use pruning. That's more a fault of sklearn than a positive decision, in my opinion. But the point is, people do plenty of good machine learning without pruning. But OK, so that's regression trees and trees. And now we're going to get into classification trees. which have a little bit of a variation. So let's go full multi-class. So K classes are easy to handle in classification trees. By the way, have we spoken about multi-class before? It's came up once. It did. It came up once. We talked about it in the conditional probability models lecture when we talked about multinomial, logistic regression, and the softmax. That was the first time that we had a method that could work with multi-class. This will be our second method. All right. So we need to come up with the way we're going to split the nodes for classification. So we had minimized the square loss. So what are we going to do? What's our loss function for deciding the split for classification? So here's just some notation. So p hat m sub k, mk, m is going to denote, it's going to be an index on the regions that a tree divides us into. And k is our class. So p hat mk is the fraction of training examples that fall into the region M that have class k. Right? So among all training examples that fall into region M, so that's n sub m, how many of them have class k? All right. So once we have that, we can, if our ultimate goal is 0-1 loss, for instance, to get the classification right, then it should be clear that what we want to do is predict the class K that has the highest proportion of training examples in that region. Right? So for any region, you just see which training example class happens most often. That's what you predict. All right. That seems very, very natural to figure out what to predict once we have the regions. So again, the question is, how do we find the regions? All right. Although we'll also note that you could predict soft classifications as well. You look at all the training points that fall into a particular region, and you can look at the relative proportions of each class, and that could be your soft prediction, your probabilistic prediction for the outcome for the Y label, conditioned on falling into that region. Is that clear? So trees right away give us hard and soft prediction, easy, and multi-class. We just need to decide how to do the splitting. All right, so here's a question. Suppose we have our partition and we choose our prediction as described before. What's the misclassification rate for an example, a new example that falls into region M, RM? What's your best guess of the misclassification rate? So p hat m sub k is the, suppose km is the class we choose. That's the most dominant class. And so, yes?
1 minus p hat.
Yeah, so if p hat m sub k of m, that's the proportion of training examples in that region of the class we predict. So the best guess for how often we're going to be wrong is 1 minus that proportion, right? 1 minus that fraction. It's our estimate for how many are from not that class. All right, good. So, all right, now to the loss for the splitting. So a natural loss for classification is of course the 0-1 loss. So first question, could we use the 0-1 loss to do the split, to decide the split? We've had difficulties with 0-1 loss before, right? Lecture 3 was all about 0-1 loss is not tractable. Let's use something else like hinge loss, logistic loss. Okay. Yeah.
You might have ties.
You might have ties. That's true. That's true. I'm not sure that bothers me too much. But yeah, we might have ties. So we'd have to be careful what we mean by what exactly do you mean by you might have ties, actually? I'm not sure what you mean. You mean you might have exactly duplicated input feature values?
Different splits that gave you exactly the same loss.
Oh, different splits to give you the exact same loss. Okay. Okay, true. Choosing randomly sounds fine. So that doesn't concern me. Yeah. So if we go back over here, so this is regression. Let's get rid of regression. Now let's do classification. So let's do the positive one. Let's do 1 and 0, because I don't have much space in the negative 1 area. So you could have whoops. OK. So here's one feature, x1. And these indicate class 1, and these indicate class 0. So do you think we could use 0, 1 loss to decide our split? Yeah, seems fine. Just as we did before, you slide over. You consider splitting at each point. And you could see what the 0, 1 loss would be. So if we split here, what would the prediction to the left be? And to the right? Yeah, very good. Right. OK. Good. This is if we have a hard prediction action space. OK. So yeah, there's no issue computationally with using the 0, 1 loss. But should we use it? Maybe, maybe not. So the issue comes back to something we were mentioning earlier, which is that even though 0, 1 loss is what we're ultimately trying to optimize, we don't have to do it in just one split. Because we're going to make a split, and then we're going to split again, and we're going to split again. And what might be optimal in a single split may not be optimal as we grow more and more nodes down the tree. So I have a little example here. So suppose, so we have 8 examples. And through some search procedure, we've found 2 different ways to split. One of them gives us what is it? Yeah. One of us gives us the split. So somehow or another, we've made a decision, xj less than or equal to s, and this sent us here. And this split us into 2 groups. So to the left, we've got 3 greens and 1 red, and to the right, we have 1 green and 3 reds. So what's the estimated what's the classification error? What's the misclassification error rate on the training examples here? Say again?
25%.
25%. So how many are wrong? We'll, of course, predict the majority class. So the misclassification rate two wrong out of how many total? Yeah, OK. 25%, great. Now, here's another example. OK. It's just splitting on something else. All right, what's the misclassification error rate on this one? Same. Which ones are wrong? These are going to be right. These 2 greens are going to be wrong. So it's still 2 wrong out of 8. OK. So here's a tie. Which one do we like better? You like the second one better. How come?
Because you can split the first big part
Okay.
afterwards.
So it seems like your intuition is that this one isn't so great. What's the error rate on this thing? 2 out of 6, 33%. OK, let's write that down. And this is 0% error rate. And this one is 25% error rate and 25% error rate. So your inclination is to go with this one. And it sounds like your feeling about it is that this one, not so great, but we can always split it again. This one, already perfect. Right? What else? Well, you could say, make the same argument at the top. Right? I could say, well, neither of these is quite perfect. I can split them again. But what happens when I split this one again? I end up with a node with just one element. And here I might potentially end up with a perfect split with still 2 elements. So this is all very heuristic and hand-wavy, and I haven't seen a kind of an argument that goes significantly beyond that. At least I have not yet understood a better argument, but maybe next year. But yeah, this is kind of the intuition that we're going for, that this splits off a nice chunk that's, they call it a pure region, where all the classes are as close to uniform as possible. So we get a nice pure region here, and this one we can split again. Whereas here, neither is pure, and in any case, if we split again, we're going to have these nodes with only kind of one example, which now we start being concerned with overfitting and that sort of thing. All right. So somehow or another, we want to be able to prefer this one. Classification error rate doesn't distinguish. That's the takeaway. And more generically, this kind of gets us thinking like, OK, maybe there's something besides misclassification error rate that we should be optimizing to decide what to split. And then as an empirical matter, you could have a bunch of these new loss functions and see which work experimentally. And certainly people have done that, and a few have risen to the top. And that's what we'll talk about now. Let's see. OK. So the terminology people like to use is the search for pure leaf nodes. Things that are as close to a single node as a single class as possible. And the notion of a node impurity measure is the terminology used basically for this loss function that we are optimizing to decide what to split and where to split. So here's an illustration of 3 of these node impurity measures. So we're in the 2-class case, just for easy illustration. And we're fixating on a particular node that has a relative frequency of class 1 of p, right? So in this case, it'd be 25%. Here it'd be 100%, sorts of things, or 0%. So as a function of p, the relative proportion of, say, class 1, what's the penalty? How happy? What's the measure of purity of that node? And so in the middle, where it's 50-50 in the node, everything is the highest kind of impurity measure, right? The green one is the misclassification error, the one that's kind of a triangle shape. Now, there's these 2 more now. Gini and entropy. We'll give the forms for that on the next slide. But the thing to notice is that Gini and entropy are much less happy to stay anywhere near a half, 50-50. They really want to push things towards more extreme values, either all zeros or all ones. So they're really pushing us further away from equal balance compared to misclassification error. So here's the generalization to k classes. I don't think we need to dwell too much on the particular form. The misclassification error is obvious. This one is a measure of the entropy of the distribution in that particular region. If you've seen entropy before, this is exactly the entropy of the discrete distribution of training examples. This one looks kind of should remind you of a variance of a Bernoulli. Okay. These are various ways to split, and one can consider these kind of tuning hyperparameters. What criterion you use to decide where to do your node splits. All right, here's a quick illustration. Here's a 4-class problem. With all of our data, we have this uniform distribution of classes. And now we are looking for a split so when we split, we'll get 2 different distributions, one on each side of this split. So in the top, here we're considering 2 different splits. So here we're considering a split there. And in the top, we have this distribution of class labels. In the bottom, we have this distribution of class labels. And we could assess the node impurity measure for each of these distributions using the formula on the previous pages. We'll get some numbers for each. And what we'll write down on the next slide, but I will just tell you now, is to assess the quality of the split, you look at the weighted node impurity of the 2 regions you end up with when you split, where the weight is exactly the fraction of points that fall into each side. Right. So here's another split vertical. And here, so visually, this looks more pure. We only have 2 classes instead of 3. And indeed, this, under the entropy measure, or here they write information gain, it's a synonymous method. So this will be preferred over this. And you can see numerically, information gain 0.69 versus 0.4, so it will choose this split. All right. Any questions? All right. So what I kind of said in words just a minute ago is like, how do you actually do this? So if RL and RR are like the right and left partitions from a split, and you have NL points in the left and NR points in the right, and QRL and QRR are the impurity measures of the left and the right, then we assess how good the split is by this weighted combination of the node impurity measures. And we would search for the splitting variable and the splitting point that gives us the smallest weighted average of node impurities. Right? So that's the search procedure for classification. Exactly the same as regression, but with a different quality of measure. Rather than square loss in each of the 2 regions, we look at this node impurity measure. And empirically, this seems to work much better than using misclassification directly to do the split. All right. OK. Any questions? So I'm going to finish the tree discussion with some general comments on trees and what's interesting about them and that sort of thing. But any questions on the specifics? Yeah.
Just quick comment. So which is in from a time complexity wise, when we are building a tree, most of the time we are spending in finding the right feature where we are going to do the split. Is it correct?
So it's for each feature, finding where you're going to split, and
not also each feature, also finding what should be the feature to split on at a particular node.
Yeah, so you have to decide both. You have to decide which feature to split on, and to do that, you have to see how good it would be to split on that feature, and to do that, you have to figure out where you would actually split. So there's no, yeah. So I don't know which is.
So on that note, I just have a question, which is, when we have a similar type of problem in general in computer science, like finding a pivot in a quicksort or something like that, what's the right? We normally use the random, select one feature randomly. Now, in case of a decision tree, is it going to work in some cases, or it's not a good practice?
Wait, select one feature random. We're going to have to search on all the features.
But I'm just saying that if I choose to have an algorithm where I'm going to randomly select a feature, split it on, then again random, somehow it's get worked out does it make sense? Means because
OK, so basically, you're proposing a new algorithm where you build a tree, but rather than finding the optimal feature to split on, you choose a feature randomly. Do you choose the splitting point randomly, or that's also OK, splitting point don't randomly. That we choose by searching, but the feature we split on is a random choice. Yeah, that's a viable algorithm. There's something called an extremely random tree, which I think is exactly that. I don't remember right now if they search for the splitting point or if that's also chosen randomly. I'm not sure. Yes, you know.
I don't know, in the random forest concept, is that the way? Because I definitely read it somewhere. That's why I'm just thinking a couple of this.
Yeah, this is connected to random forest. Yeah, we'll come to that. But just to give you a sneak preview, in random forest, you build a lot of trees. And each tree is built where instead of looking over all features for what to split on, you randomly sample a subset of features. A limiting case would be a subset of size 1, as you're proposing. But typically in random forest, the subset might be square root of number of features or half the number of features. 1 would be an extreme case. But 1 has been proposed, absolutely, for random forest.
Just another comment, which is when we are again selecting the features, I think I have read somewhere, I don't know whether it makes sense or not, is kind of you can eliminate the number of features if 2 features are correlated to each other. If you figure it out how to find correlation, so you can basically shrink the number of, reduce the value of d in this case, so that.
You love to throw out features. That's always your favorite question. I'm not so familiar with that variable elimination approach in random forest. Yeah, it's interesting. In trees in general, you can get a masking effect, which may be of interest here, which is suppose you have 2 features that are highly correlated, but one is a little bit better at doing the prediction than the other. So the one that's not as good will never be selected for a split, because the other one will always be better. And so that's referred to as masking. And it becomes relevant when you try to extract a variable importance measure for variables from trees. And you basically, one way to do it is at every split, you've chosen a feature, and you can see how much does the kind of node impurity get reduced when you do that split at that location. And you could kind of attribute that to that particular feature. So in a given tree, you could kind of count up what's the total amount of node impurity reduction attributed to each feature. And then that's kind of a very heuristic way to assess importance to each of your features. But then if you have a feature that's almost as good as the best feature, but not quite, it'll get an importance of 0 because it's never chosen, because the other feature is always a little bit better. So anyway, these are things that come to mind when you suggest throwing out features. Yeah?
Although you might find that at different stages of the tree, one was better here and the other one ends up being better there, so you end up needing to keep both of them.
Yeah, at different stages of the process, one might be better, the other might be better. Absolutely, yeah. All right. So a few comments I wanted to make about trees in general. One great thing about trees is that they come kind of with a built-in, not quite built-in, but we will propose now a way to handle missing features very naturally, which is very nice because any method then built on trees like random forest or gradient boosted regression trees also will handle missing features if the base tree handles missing features. And missing features are nice to have a solution to. Right. So how do we do it? So one approach is you don't handle missing features. You just throw out your data points that have missing features. Okay. Another approach, impute values for things that are missing. So maybe the simplest thing would be to plug in the mean or the mode of that feature anywhere it's missing across the other training examples. Another approach is if it's a categorical feature, you can add in a new category missing. All right, that could be fine. And this could be useful in this situation, which is common, where things aren't really missing at random. When they're missing, there's maybe a reason it's missing. So if you think there's signal in the fact that a particular feature is missing, you should act on that by making that exposing that in the feature. But if your features are missing kind of at random, then in trees there's a very there's a proposed and common solution called using surrogate splits. So the idea of a surrogate split is first you find your best split. You find the feature on the splitting point that gives you the best split. And you see these 6 guys go left and these 2 guys go right. And in searching for a surrogate split, what that means is you say, all right, well, suppose I don't have access to that feature. Let me find another feature that, and there's 2 ways you can go to here. One way would be, let's find the second best split in terms of our kind of impurity reduction, all right? But that's not the surrogate splitting approach. The surrogate splitting approach says, OK, the rest of the tree is going to be built on the assumption that we're splitting on the best possible variable. So what we really need to do is find another feature that will help us approximate this split as closely as possible. So in a surrogate split, you find another feature that, and you search for the next best feature that can approximate this exact split as closely as possible. And so in terms of kind of maximizing the number of points that are set in the same direction as the kind of the optimal split. And you could do that. You could find the optimal split for all your features. In other words, you could find a surrogate split for each feature. And so even if a particular input example has only one feature present, you could still decide which way to go. You can rank the features by how well they can reproduce this original primal split. And so every node would have the primal split. And then if there's d features, d minus 1 additional splits in a ranked order as backup if the features are missing. Is that clear? Yeah. OK. Great. OK. So that's missing features. That's a very nice aspect of trees that they have that way to handle them. Unfortunately, sklearn doesn't implement that yet. I think that's a pull request or something. For trees, I think R and some other languages are just a little bit more advanced for trees. OK, categorical features. We've only spoken so far, really, about continuous features where you choose a split point. But what I mentioned for categorical is you basically group your categories into 2 groups. So red and green could go to the left, and the rest of the colors go to the right, for instance. So this feels potentially intractable. You see why I'm worried about intractability. If you have q possible values for your categorical variable, how many different ways can we split those categories into 2 only, for starters? Yeah, I mean, something roughly exponential. Maybe you can get rid of half of them by symmetry, and maybe you don't care about the one that's all in one. OK, but roughly 2 to the q. That sounds intractable. And of course, generically, it is. But there's this great theorem from the original book on CART. So CART, there's a book published on CART in 1984. It's like 200 pages. The font is hilarious. It's like very old school computer print font. And it's by the authors of Bryman, Freeman, Olshan, and Stone. And it's a pretty amazing book. I mean, they proposed the method, but these guys were real masters of machine learning. And there's so many great ideas in there, well beyond just this algorithm we're talking about. So one of the things in that book is this theorem that says you don't have to check all 2 to the q minus 1 splits to find the optimal one. And what you can do is look at each category, and you assign it a number based on, and this only works for binary, only for binary classification. You assign it a number based on the proportion in class 0 from that category of the variable. So suppose it's red, green, and brown. So you go to the red category, and you say, what fraction of my training examples have class 1? that have red for that feature? What fraction have class 1 for green? What fraction have class 1 for brown? What fraction have class 1 for blue? And you assign a number to each category. And then it turns out you can, just like we did for the regression case, for the continuous variable case, we can sort based on those proportions, and the split, the optimal split will always happen between, let me just write the example. So red, green, blue, orange. And I'll write proportion in class 1. All right. So red, green, blue, orange, this is like a particular feature, x2 for instance, color. Right? And for each of these values of the feature, 4 discrete values, there will be a proportion of training examples that have class 1. So maybe it's, and we can sort them. So this is going to be in sorted order. Oh, that's not going to be right. What do I have to make it? 0.9, 0.6, 0.04. OK. All right. So the theorem is that the optimal split into groups is always going to be in one of these places. So we only have to find these proportions, sort the numbers, and then check these or q minus 1 possible splitting points. So miraculously, we can avoid this exponential search over splits of categories. This doesn't work in multi-class. There's other approximations you can do.
Yeah. Do one-hot encode for multi-class?
Great question. So what about one-hot encoding? So we have these categorical variables. Can we do one-hot encoding? So one can. It turns out, and a TA made a really nice Jupyter notebook kind of really elaborating on this exact point that I'll link to. Turns out one-hot encoding is not nearly as good in many situations. I'll give you a quick flavor about why. Let's take an example of lots of categories. So suppose there's 20 categories. All right, that wouldn't give this method much trouble. Right? You just split. But with a one-hot encoding, remember, we're only splitting on one variable at a time. So even if you've distributed things as evenly as possible, a particular category will at most split off like, what, 5% of your, in the worst case, any split on one of those 20 categories will always have one of the regions have at most 5% of the data points. And so it's hard to get a big reduction from using those categorical variables when there's lots of categories. So that's one issue. Yeah.
Isn't this example categorical?
This is categorical, yeah. But so here, let me just make clear what we end up with. Here we're going to find the split between categories that gives the best reduction, and we could end up with this split where red and green go to the left and blue and orange go to the right. But if we did a one-hot encoding, we can only split on one of these variables at a time. So the split would either be if you're red, go right. If you're not red, go left. If you're green, go right. If you're not green, go left. And what I was getting at is that if you have, for instance, many categories, then one of your regions after the split is going to necessarily be small, because one of the regions will only correspond to kind of one of the possible category values. Whereas with this type of splitting, we can group categories together so we don't end up with regions that are too small too quickly. Follow up?
So is the point that you can have categorical variables, you just shouldn't one-hot encode them?
We absolutely can have categorical variables. If you have nothing better to do, one-hot encode. That is, again, what scikit-learn does. Beware, though, if you have lots of categories. If it's like 3 categories, I wouldn't worry too much. If it's like 10, 20, 40 categories, that's when you start to get problems. And if you don't have special kind of code to do this type of splitting, I would recommend perhaps grouping by hand your categories together into bigger categories.
Well, if you never want Q to be large, then there's no benefit of this, reducing 2 to the Q minus 1 to Q, is there?
Well, I see. So you're suggesting, that's a nice point. If your Q is small, do a brute force.
Well, I'm not saying that we have to, because this is obviously better than 2 to the Q minus 1, but I'm saying that then suddenly this is much less novel as it sounds, because if Q is larger, like around 10, then it breaks down anyway.
No, this works fine for Q large. It's one hot encoding that doesn't work nicely. Yeah.
This doesn't work for multi-class outputs.
That's true. Well, now I'm confused. Isn't that a multi-class output?
No, the output is 0, 1. Sorry, this is classification. This is a feature that's multi-value. Yeah, sure.
Suppose, could you cluster to create synthetic classes out of your multi-class inputs?
So your suggestion is, can you cluster? I mean,
feature engineering.
So yeah, so I don't know the exact way that should go, but yes, in some sense, collapsing categories might be a good way to go. Yeah. All right. Okay. What about statistical issues from having a category that's very large, which is to say has many different values? The limiting case I always like to think about is, what if row number was accidentally put in as a feature? Right? Your table. So a tree would have the ability to kind of pick off every row number and put it in its own class. So one has to be careful of these things. Yeah. Okay. Questions? Ready for the next bullet? All right, next bullet. So to now, we've actually only spoken about linear methods, or linear methods on top of nonlinear features. So let's compare to trees. So here's an example of 2 different classification problems. On the top, these colors are a little bit close, but here you have a kind of an optimal separating line in the top. And so on the top left, you see a linear method can separate these 2 classes piece of cake. But a tree method, which gives you these regions that are rectangular, has to work a lot harder to approximate kind of that linear Bayes optimal separating region. Conversely, here where the class region is a square, the linear method has a hard time approximating that, and the tree can nail it no problem. And so this is highlighting the fact that the hypothesis space of trees and the hypothesis space of linear functions, or linear classifiers, are good for different things. And so one should bear in mind the type of prediction functions you're going to end up with from trees or from linear methods. Question?
So the axes on these graphs are...
The axes, these represent input space, so x1 and x2. These are features. And then the color is the label.
So it seems that you could argue that given a proper transformation of a combination of features, that you could transform for example, a linear problem into something that would work better for a tree problem. Like it's sort of like the fact that that line is slanted for this space.
Ah, OK. So you're suggesting that even though tree has a difficult time with this, you're noting like, oh, but if we rotate the input space, we transform the input space, it would be easier for the tree because we could. Yeah, so true, but the issue is, of course, how do you know the transformation that makes it easier for a tree? And I don't know.
If it's that obviously linear, you're probably not going to try a tree to begin with.
So it's in general, it's hard to see when you, especially when you have high-dimensional input spaces. You can't do this type of plot. I mean, I love these types of plots where the input space is 1 or 2 dimensional, so you can kind of see something. But when you actually apply machine learning, you usually are doing it on a high-dimensional input space, and it's hard to get these types of insights by visualization. Yeah.
Can you combine them, like do a tree of where the leaf nodes have linear fits, and then I guess you have a different loss function at each step when you're.
Interesting. Yes. So could you, rather than having a constant prediction in each of the leaf nodes, could you, for the training examples in the leaf node, fit a line or something? Yeah, absolutely. You might want to adapt your splitting accordingly. Yeah. Yeah.
You're looking for things that, like, you don't necessarily want things that are close to each other in an average sense. You may want things that are close to each other from a slope sense, I guess.
Yeah. I don't remember the name, if there's a name for what you're describing. Not sure. The Hasty Tips Johnny Friedman book would be a good one to look in for that. All right. So interpretability. People love interpretability of models. And is a tree interpretable? Kind of, sometimes. If the tree is small, then it's fairly easy to describe what's happening. You know, you look first at the first variable, and then the third variable, and then fourth variable, and then you can kind of explain it if the tree is small. If the tree is large, good luck. It's hard to, even though intuitively you know what's happening, if you want to actually explain the decision tree overall, it's not that easy for a large tree. But if you end up with a small tree, it could be very nice and intuitive. But another thing, this is kind of like the reverse of your suggestion, is that you can look at a tree building procedure as a way to discover nonlinear features. So when you build your tree, you end up with a partition of your input space into rectangles, right? You know, or something. And you know, this square represents input space X. And what you could do is make a new feature for each of these regions. I think I wrote that down here. So like the indicator that an input X is in region M could be a feature that you use in another model. So imagine you wanted to make prediction functions of this form. A tree has prediction functions of this form. But what you could consider doing is fixing these indicator functions as features, and then using another method to find CCM. For instance, this is a linear model now. With these indicator functions fixed as features, this is a linear model. You could use lasso regression, or ridge regression, elastic net. You could add in additional features. You can add in your linear features now. So the tree can give you the nonlinear features by taking regions, but then you could add in, if X has kind of continuous features, you could add in x1 through xm and squares and cubes and all those terms. So that's kind of a mix of the features that are on when you're in these odd rectangular regions with features that scale in the usual way of linear multiples of the raw inputs. So you can mix and match these things. And we'll see this again with neural networks, that you can look at these nonlinear methods as a way to discover features that you can then take and use in another context, like a linear method or something like that. All right. Because until now, features are always hand-engineered, right? There was never any machine learning to discover nonlinear features. So this is also a first, you can view this as our first way to do a little bit of automated feature discovery. All right. And I think the last main comment I want to make about trees is to note that there's no geometry in trees. There's no inner products. There's no distances. All these things that show up in linear models are completely absent from trees. There's only really one thing that we assumed about kind of our, what do we assume to use to do trees about our, say, our input space?
That you can divide the input
Yeah, so it was an assumption about every feature of inputs, every coordinate of input space, every feature of input space. And we had kind of two versions of it. One was that each feature was discrete, in which case, and finite valued, in which case we could partition the possible categories into two parts. And the other version was if it was a continuous feature, it has to be ordered. So we have to be able to sort them and order them. So it would work fine for non-continuous things that are ordered, like small, medium, large. That would be fine. You could sort them, and you know the split between them. They don't have to be numeric valued even. There is nothing in the tree building procedure that actually used the numeric values at all except to sort the feature values. So we just need a way to sort the feature values. If you're building a tree, does it make sense to center and scale your data, your features? Doesn't matter at all. No, doesn't matter at all. OK. Any more questions on trees? So then we'll take a break and move on to ensemble methods.